Hey, alright, we're continuing with the old bootsector code here. This will be part 3, and where we last left off, I believe we're printing both strings here, our two test strings. We changed the color in the video mode in the BIOS with the interrupts, and yeah, we're still printing tests. This is also a test, so that's good. Always make sure you didn't break what you last did, so you can start off right. So in this part, I'm going to externalize our print string here, our code, our function, into an external file that we can call from our main bootsect assembly here, and then we'll probably get into printing hexadecimal strings for just because we can. It'll be useful for debugging or seeing addresses, that type of thing. So inside assembly, how do we call other files from our one assembly file here? Well, we need to include them somehow. And I'll just, clue you in there. We're going to use an include directive here, which is just in flat assembler here, use include, the word include, and then the name of your file. We'll make one called print string. We'll just call it print string.assembly. I think in NetWide assembler, you prep in the include with a %, and then these are in double quotes, although maybe single quotes doesn't matter in that. But in flat assembler, just include in the single quotes, and this will basically take the source lines that are in this file here. So like these are all source lines in our main bootsect file, right? But what include does is take the source lines in this file and just prints them like right here. So when you assemble this, it'll be just like writing all this source code at this point in this file. But it's often more convenient and better to just separate out your duties here and have print string in a separate thing than if you use more than one file and include it. You only have to change it in one place in case it needs to be changed instead of going into every single file and changing. So that would be nice. And maybe you don't want one giant 10,000 line file if you can help. So that's good on there. So I'm just going to have another file in the window. We're going to call it our print string .assembly. Prints character strings in BX register. That's what we're going to be doing. We're going to be taking basically the same code here, we're just moving it into an external file. But we're going to take our code here, print string and endprint. We're going to copy it and put it over here, hey. So that's all good, and that's pretty much all we need to do now, because this should work by default. That should be all we need to do. The calling will still work, since it's the equivalent of putting these source lines in here by using the include. Calling this will still work because it'll just be like calling it. It's still there, and it'll return at the return, and that'll all be good. I think we'll want to do, I'm just going to put a section here, included files. I think we'll want to put this after our jump statement here, if I remember right, because it's kind of like part of a data section, sort of. So in program, I'm going to have be at this point in the code, which means we don't need this jump here anymore. And if you don't do that, if you just leave it how it was, let me put in program here. If you just leave it how it was, I think it'll sometimes when you're running box or the emulator, it'll keep looping through non-existent memory sections until it reaches the next executable part of code, and we just want to prevent that. Try to be more clean and clear here. Of course, I got my coffee, 2 cups a day right now, building up that tolerance. But yeah, this should still work fine like how we were doing. Let's see, make sure I don't lie to you, right? Include file not found. Well, that's because we didn't save it yet. There we go. If you actually write the file, then you can use it and it's saved. Magic, right? So this should do the same thing. And it does. Test also a test, so we're good. Always make sure your stuff still works. If you can make an automated test suite, that's even better, but we're doing everything manual for now. But that just shows that this works. Now, when you're doing externalized files here in assembly, I think good programming practice would be to save and restore your registers so that they're not messed up. Like we're using AX and BX, we're putting values into there. If we did more stuff beyond this point, we wouldn't want it to be messed up from any external function calls, right? That'd be bad. So to do that and prevent that, we can do a thing over here such as push and pop A. And these are instructions that do, what do push and pop A do? It pushes all registers onto the stack. So, your CPU has an extra area of memory it can refer to. It's sort of a vague area called the stack. And basically you push stuff onto the stack And it'll be, if you can think of like plates maybe stacked up, like, you know, you got a pile of plates here, you push something onto the stack, you put a plate down, you pop it off the stack, you take the plate out. And that's how that works. But we're basically pushing all the register values onto the stack, and then it's copying the values in them. So if you mess with them here, it's still going to be fine. You're just copying them to the stack, and then at the end we're going to pop them back out and restore our register values before returning. And that just makes sure they're clean and clear inside our original caller for the function, so we don't mess them up in our external function calls. I'm going to put store all register values onto the stack and restore registers from the stack before returning. Okay. And we don't want to push all the register values onto the stack every single time, because we're going to be moving letters into AL, and that'll just be pushing the letters in AL onto the stack every time, and we won't have expected results when we call other print strings for other strings after the first one. So we're just going to use another label here call it print character, and then instead of going to print string, we'll go to print character for the loop. Okay. So, and to prove that pushing and popping values works, we'll do this again. And we're good, it works. So that's all nice and tidy now. So that's basically external function calls in a very short nutshell. You just move your source code. It's the equivalent of including the source code here. And this file doesn't have to end with ASM. I just did it, so I'm keeping them sort of together. I think some conventions call for using your included files inside an include folder or directory and putting .inc for the file suffix, but I'm just keeping them assembler for now. Okay, so for the next part of this, we're going to be printing hexadecimal numbers, or hexadecimal values, and we're going to use a separate external file here, another one, just to print hexadecimal. It's going to call our print string here, because we're still going to be printing ASCII characters to the screen. You can't really print straight hex values to the screen. You can, but there'll be different values in ASCII, as you'll see. We have to convert hexadecimal to ASCII to get the valid character we want to print, and then put it to the screen using here, because they'll just be, you know, character values. So that's what we're going to do. We're going to make another file. We're going to call it print.hex.asm. I'm going to say it prints hexadecimal values, digits, characters, whatever. Prints hexadecimal values. We'll say using print string ASM. Now we're going to use another register here to use our hexadecimal, because we're going to store them. We could store them in a variable and pass that too, or another memory address, but I'm just going to use a register because I think it's still kind of faster than setting up a separate memory location and using that. So we're going to say, let's use DX, using register DX and our other assembler file here. So we'll need another include file. We're going to include print hex.asm. And the way to do this is we have to convert hexadecimal to ASCII. If you look up the ASCII code tables and stuff, you'll see them there. But to convert them, I'm just going to put short versions here. I have a thing printed out. I got my references for what I need to do for this. But basically, you'll find hexadecimal 0 to 9, and then for 10 to 15, because it's hexadecimal, goes up to 16. You have A through F. So it goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then 10 is A. 12, 13, 14, 15 is B, C, D, E, F. So to convert these between, you have the ASCII people made some good stuff, but the characters you see printed to your screen are not the actual numbers, they're different. So, but to print the characters 0 through 9, if you want the equivalent in hexadecimal, it is hex 30 to hex 39. So if you move a hexadecimal 30 into AL, and you use integer 10 to use teletype mode, 0x0e, and you move hex 30 into AL and you print it, it'll be a character 0. It won't be the value 0, the number 0, or null, it'll be a character 0. So that's cool. So to print each part of hexadecimal, we'll need the numbers and the letters. The numbers will be garnered by that, hex 30 to 39 for ASCII, 0 to 9 characters, and then the letters, you can do upper or lowercase, they're separate ones. So uppercase A through F comes first, and that is hex 41, right? Yeah, hex 41 to hex 46. And then if you want lowercase A to lowercase f, will be hexadecimal 61 to 66. I'll just put that there as a reference so we don't need it later. So we'll start off here, our print hex, we'll do as like we do the other one. We're gonna push all the registers, store, save, we'll put save. Save all registers to the stack. Okay, and at the end we'll return. I'll just put that at the end here. Return. We'll put return to caller. Before that, we're gonna do pop a, restore all values. Restore all registers from the stack. Okay, before we return, because it's good practice. Okay, so basically what we're gonna do is send a hexadecimal number here into a hex number that is contained within DX, and we'll send it to here. So we're gonna leave our print strings alone, but we're gonna use a hex test, I think, and do this. String 2, let's change. Instead of also a test, we're gonna do hex test, and then put it after the space here. And our print one, we're gonna do, I don't know, string test or character test or something. We'll do character test. Testing. Hex test, we'll do something else. All right, and we're gonna have another thing here. Actually, no, we'll put that into our print hex and keep it separate. We are gonna be using the DX register, so let's set that up. Let's put it here. We'll move into DX, our hexadecimal numbers. So I'm gonna do something with numbers and letters so that we get both sides so we can see it works right. So we'll do 12AB, I'll put sample hex number to print, and then we'll call our print hex function that we just made. We're gonna move this into DX, and then we're gonna call print hex. So we need to access it within DX. We need to change the hexadecimal value 12AB into ASCII character values 12AB for the characters to print to screen, and then we'll print it out. So to do that in our print hex thing here, I'm gonna have a sort of data section in this as well. Data variables, whatever you want to call it data. We're gonna have an empty hex string that we're gonna use. We'll just make it an empty byte here, end it with 0, because we're gonna put this into BX and send it to print to the screen. Since we can't print regular hex values, we're gonna manipulate a string here to equal those hex values, and then use that string to print as BX using our print string assembly other function. So to do this, to go through each one of these 4 characters here, DX will be 12AB. We're gonna need to get it basically one sort of digit, one value, one character at a time, and put them into their required places into here, right? So to do that, we can use a loop. We can use another way to do a loop, and to that we're gonna use our 4th general purpose register, which thus far we haven't used, and that is CX. CX is traditionally used as a sort of a counter, an iterator, as you will. So what we're gonna do is initialize CX to 0. I'm gonna put initialize loop counter. We're gonna use CX as a loop counter here instead of making another just counter variable. We already have a register, might as well use it, right? So we're gonna do that, and then we're gonna have a loop. I'm gonna call it hex loop, I guess. I like to use underscores in these, so we'll do that. We'll do our hex loop here because we're gonna have a loop. And then this will be, I guess, end loop. I'll do end. We did end print on the other, right? So I'll do end hex loop when we want to end it. Okay, we'll pop it and return. Okay. So inside of our loop, we need to get each character, convert it to ASCII, put it in our empty hex string here, put it into BX, and then go print it out. So what we're gonna do on each loop iteration is compare our iterator. We can't really do a for loop in one line, so we're kind of separating it out here, as you can see. We're gonna compare CX to 4 because we're still in 16-bit real mode. Each hexadecimal digit is 4 bits. We have 4 of them, so we're gonna go through each one. That is 4 times. So we're comparing our loop counter to 4. If we reach 4, we're done. If not, we need to keep going. So I'm gonna compare to 4. Are we at end of loop? And then if so, we're gonna end the loop. So end hex loop. Gonna jump to it. But if we're not, we're gonna continue on our main loop body here. So we're gonna convert DX hex values to ASCII, and then we're gonna move them into BX later. move ASCII value, or ASCII character, I guess, into BX string. Okay. So we need to convert our hex to our ASCII. Now, how do we do that? Well, we're going to use our AX register here, or any other. You can make a valid memory location too, but we're just going to use AX here. Move DX into AX so that we can save the value of DX and just manipulate, you know, each one that we do. Otherwise, you could maybe push DX and then manipulate its values using offsets or other things and pop it back out and save it. But this is just one sort of simple way to use it. Get my brain juice going. Okay, so we're going to move DX into AX and use AX as sort of a working variable, working directory here. And now that we have our hex within there, you can do this a couple different ways. You can use shift right, shift left, which will shift right is SHR. We can shift this we're using AX, which will basically move the values in AX 4 bits to the right. We're not going to be using this, but I'll just show it. So if AX was, I don't know, 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, 1, right? Because 16 bits is one word, and that's what our register length is. So if it was this, and we shifted it right 4, then the shift right would make it equal this. It would put 4 zeros here. You're basically shifting the whole thing right 4 bits. So these will be zeros, and then you'll just be left with this. I think these ones go into the carry flag, if I remember right, but we're not dealing with the carry flag at the moment, so we're not going to worry about that. That's where unseen values go, I guess, and then they're restored from the carry flag if you shift left, I believe, but I might be wrong. But anyway, that's shift right. If you don't understand it, I'm sorry. I'm not good at explaining. Instead of that, we're going to be anding, bitwise anding. So if you know Boolean logic or discrete math, you'll be good here. If not, then I can try to explain it. But we're going to and our value in AX, which at the moment is 12AB, hex 12AB. We're going to and it with hex 000F. So we're going back to front. We'll be looping through. We'll be taking the final digit, converting it, and then the second to last, third to last, and then our final one here to begin it. We'll be moving it into here and into BX. So anding by 0 and F. Well, F, hexadecimal F in binary is 4 ones, and hexadecimal 0 is 4 zeros. So in effect, by anding this, we are getting the first 3 hex values and making them 0, and then the last one will be our character. In this case, it'll be B, but the first 3 will be rendered 0 in this one, due to the fact that we're bitwise anding them. So our bits here, well, they're 1, 2, A, B, so I think hex 1 is what? That's 1, and then 2 is 2 is that, or if I'm converting to binary here, it's very bad. Hex A is 10, so it'd be a 2 and the 8, so it'd be 1, 1. Maybe I should separate these out, that'd be better. 2, 3, 4, I think that's hex 10. And then B is 11, so we would need 8, 2, and 1, so that would be 11. Okay, so that's 1, 2, A, B in binary, right? And if we're anding this, we're anding it with this value here, 0, 0, 0, and F. And what this will do is basically make all of these 0, because 0 and 0 is 0, and 1 and 0 is 0, 1 and 1 is 1. So, you know, these will be 0, these will be 0, these will be 0 because we're anding them, but the last one will keep whatever value it is in binary, and then thus in decimal or hexadecimal, because we're anding it with all ones. We're keeping our B value here. It's not going to change. The ones in binary will stay 1, 0, 1, 1, and then all the rest will be zeros, including this 0, because we're anding them all. So we'll basically be left with our final character here. This will be equivalent to 000B, like I said, or 0B if you want to disregard the first 3. Basically, that's what we're doing here. We're anding them. So let me say turn, I don't know, first 3 hex to 0, keep final digits to convert. So if that doesn't make sense, I apologize, but hopefully that made a little bit of sense. My discrete math teacher in college wasn't very good, but Boolean logic I kind of gathered on my own and understand it well enough to to understand it. If you convert things to binary and then do it like that, then bitwise logic makes a lot more sense, such as this anding. So I recommend that if it's still kind of confusing. Convert your stuff to binary and then, you know, work it out in your head. Usually it makes more sense. But that was a long spiel and digression. I apologize. Let's move on here. After we and we get the last digit, what we want to do is see what last digit we have, our last hexadecimal digit. In this case will be B, but it could be anything, right? Any valid hex. We're going to compare that. It'll be inside AL. We're in AX, which is 4444, because hex digits are 4 bits. So the first two I think should be in AH, and the last two should be in AL. And since we're comparing the last digit, it'll be in AL. So we're going to compare that to hexadecimal. What are we comparing it to? 39. So why are we comparing it to 39? Well, 39 hex is our last number in Ascii. Is the hexadecimal value we're using 0 through 9, or is it A through F? And if it is less than or equal to 39, it'll be hex 30 to 39. It'll be 0 through 9. If it's greater than 39, it should be A through F, effectively, because we won't have any hexadecimal. A through F will not be less than 39. It'll be greater. It'll be 41 by default. That's basically what we're doing. So is hex value 0 through 9? Or A through F, which is greater than 39. 0 through 9 would be less than, can't type, less than, equal 39. You like how I keep looking at my keyboard because I'm not good at touch typing? That's the best. Or A through F. If it's less than or equal, we'll do this first. If it's less than or equal to 39, then it's a hex number, and all we need to do is add hex 30. So less than or equal, we'll go to a hex number thing that we'll put here, hex number. And then we will add hexadecimal 30, because whatever it is, it'll be hex 1 through 9, and then we'll add 30. Or wait, no we won't. If it's less than or equal, it's already 39, sorry. If it's less than or equal, it's already 39. It's hex 30 to 39, so we don't need to do anything to it. It's already the number, and we can just move it. Let's do move into BX. Let's do this instead. Because if it's hex 30 to 39, it'll be less than or equal, and we can just move the number into BX. Otherwise, we'll have to add and then move it into BX. So let's do this. Move into BX. So if it is greater than 39, then it is hexadecimal A through F, and we'll have to add a value to it to have it equal the Ascii thing, A through F. So the greatest it can be is hex 39, the lowest it can be is hex 30 before we add something to make it a letter, which that doesn't make sense. But what we're going to do is add hexadecimal 7 to get our Ascii letter A through F. Okay, so why would adding hex 7 at this point give us our Ascii A through F? Why do we have to add that at all? Can't we just add 30 since it's greater than 39? No. You can add 30 if you already have the hex 30 to 39, and that'll give you the required Ascii character. But hex A through F, uppercase at least, is hex 41 to 46. Now when you get to a character, let's say we have hexadecimal A. A is 10 in decimal. The Ascii value for hex, for A, the Ascii value for A in decimal, we'll do A is, I'll put dec, in decimal is 65, but the hexadecimal value for A is decimal 10. So to get to our Ascii value of A, we need to add 55, and it just so happens to turn out that hexadecimal 55 is, or well, decimal 55, not hex 55, I'm sorry. Decimal 55 is hexadecimal 37. So we can add 30 by default, which we're going to do here, which we haven't done yet. Let's do this here. And if we do that, then we'll get the numbers, but to get the letters, we have to add another hexadecimal 7. So if we have a letter, we'll just add 7 to it, because 7 plus 30 is 37 in hex, and then that gives us our required starting value of 65, and then up to the ending 46, whatever that is in Ascii. So that's why we have to add the extra 7 there. That probably doesn't make sense, but that's what we have to do. I can put it here. 10 plus 55 equals 65. So I'll put hex A plus 37 equals 41. It doesn't make sense, but it works, so don't worry about it. That's okay. But that's why we have to add the extra hex 7 there to get the ASCII letters. We'll either add an extra 7 and then go here, or just go directly here if it's a number. So first we're going to add 30 to get to the ASCII numbers. As you can see up there, the hex values. Get ASCII number or letter value. And now we have to move this into our BX. So how do we do that? Well, move it into our string. Well, we have to put our string in BX first. So what we're going to do is move into our BX register. Since we can mess with it now, since we stored them all up here, to move into our BX register, we're going to basically move this string and then put in the value into this point in the string. So our base index at BX, we're going to move into that the memory address of our hex string. All right, plus whatever the length of our string is. Since we're moving from the back front into here, we're moving from the end forward. This value in this string, if we see this as the base string at a 0 offset, we have to add 1, 2, 3, 4, 5 to get to the end here. Because we'll be starting at this. If we just move the hex string into it, we'll be doing this right here. No, we want to print the 0x to signify to the screen, to the user, that it's hex, but we want to manipulate the ending value because that's what we're taking up here. So to get into that, you have to add 1, 2, 3, 4, 5 to the base address of hex string. We're going to move that into BX. And also this is where the loop comes into play, because then we're going to subtract. You have addition and subtraction in this. It's great. We're going to subtract our loop counter value. So we're going to put base address of hex string plus length of string. And then we're going to subtract, I don't know, loop counter, iterator. What did I call it here? Index. I'll just put loop counter. And what this will do, since it starts at 0, it won't subtract any from this. So we'll just get the first one there. But then the next one, what we're going to do is add 1 to CX to increment the counter. And what this will do on subsequent loop iterations is we'll start at 0 because we moved that into there to begin with. Then the next time it'll be 1, so it'll subtract 1 from this ending value, and the letter will go into BX here, and then we'll subtract 2, and then 3, and then that should work because when we reach 4, then it'll jump to the end of the loop, and we won't worry about it at that point. So that's what we'll do here. We'll add 1 to CX after we subtract it, and then we're going to move that value into BX. We have the right address of the string in BX now. So what we're going to do is move the value into there so we can print, these characters. So how do we do that? We need to move into BX, into the actual value contained at the memory address that we're pointing to. We're going to make equal to AL, which is what we converted our hex, into ASCII. The ASCII equivalent for the hex value in AL. We're moving into BX. So the address at BX is pointing to here, but the value we want that to equal, we use the brackets, we want that to equal AL. So we're putting that value here. So for this one, it'll be B. Okay, then after we do that, we want to get the next hexadecimal character in our DX here. We want to go to the A and then subsequently to the 2 and the 1, right? So to do that, we're going to use a different instruction called ROR, but this means rotate right. We're going to rotate it by 4 bits. Rotate right by 4 bits. And what this will do is, I'll put it here, I guess. What this will do, since we're starting with 1, 2, AB, after the first rotate right, it basically takes the ending digit and it rotates it around. We're going from the right, so we're going clockwise since we're doing rotate right. So we're rotating this B up to the front because we're going by 4, and we're using DX. DX has this value. We're going to rotate right, so we're taking the ending value first by 4. So it'll go 1, 2, 3, 4, counting from a 0 offset. So after the first rotate right, it's going to equal B12A. After the second one, it's going to equal AB12. And then after the third one, it's going to equal AB2AB1. And if we go through a fourth iteration, it would be back to its original value, which is 12AB. So it takes the ending value, basically clockwise rotates it four bits to the left. And I think it goes through the carry flag, if that makes sense. It puts these in the carry flag, then puts it here and puts them back or something. Anyway, that's what this does, rotate right. Rotate left would work the same way, except in reverse, kind of counterclockwise. If you can think of it like that, that would be moving the 1 to the end and then shifting these left. So it would be, 2AB1 and then AB1, 2, and then, subsequently. But we're going to do that. And that gets our next hexadecimal character. And then we're going to go back to our starting loop here. So we're going to jump to hex loop. And then that'll continue our loop, I guess. Maybe to make this a little clearer, I'm going to put this down here. Add CX1. Increment the counter and then go to the next loop. Loop for next hex digit in DX. This we did move. I typed it all above it. So we're moving it into the BX string. And this should put our full hex 12AB into BX. And then we should, we'll print it out. So that should be all right. So at the end of this, BX will have this string filled out with these 4 digits here. And that'll be nice. And then we can print the string like we do normally. So at the end of this, we will have hex string, so we're going to put it into BX to move the full thing into BX. All right, so to better explain this, we've taken BX, we've indexed it. We've put in the address of hex string there, but we're indexing actually these four positions into BX. So we're taking the address of this one to begin with. We're putting it into BX, and then we're putting the value at that address into BX. So BX would just equal this at the moment. And then on the next loop iteration, we're putting this in, and then this, and then this. So at the end of this, BX would equal these 4, pretty much. These 4 characters. Now, if we want to include the 0x, then we basically put the whole of hex string, put the beginning address into BX. So that's what we're going to do here. We're moving the address of hex string into BX so that BX would point to this location, and it would include the 0x. Now normally it would also include all these zeros, but since we made those values in BX, our hex numbers, those will still be, 12AB in this case. But this just makes sure that we point BX to the beginning of hex string that it's pointing to, so it'll include the 0x here, so we don't have to add that inside our print string function. We can just print the string that BX now contains. So all that's left to do is call print string, which if you remember before, that works because including is the equivalent of putting the source lines in here. So we'll already have the print string source lines effectively within this when it's assembled. So we're just calling it as normal. And then we'll pop A and we'll return to wherever print hex was called in this case, which will be here. And then this will jump and end. So we should, fingers crossed, be good to go at this point. I don't think I have any more notes here. I'm just making sure. No, I think we're good to go. So let's try this out and see if it works and prints our hex. If it doesn't, then I'm wrong, like this. Illegal instruction. Beautiful. So where's this at? 24. I did not put a colon. Well, you should put colons for your labels so that they count as labels and it works. That would be something. All right, we're good. So this should print our character test testing as I'm pointing at the screen, and should also print hex test and then our 0x 12AB. And it does not, it prints nothing, so that's good. Okay, so I figured out a couple of things that are wrong with what I'm doing here, so I'm gonna fix these for you here and tell you what I did. So we had the add hex 30 down here. This needs to be before you compare because we're comparing at this point if we're equaling hex 30 to 39, whereas before our first value hex 12 would be hex 1. So before we add, or before we compare it to, if it's 31, we need to add 30 to it, duh. So don't compare it down here, don't mess up your SpaghettiOs, put it up here. And then we can compare it, because after we add 30, a 1 through 9 value would be, 31 through 39, and then we can rightly compare it, and that'll work, okay. Now the other thing that I wasn't getting printing from is because you see our print string thing here, we're assuming that AH has already been set up for our teletype output, and it is not. And since we're affecting AX within print hex, we need to put it in here instead. So I'm going to move it out of here. CXO, and then move it into here. We'll set it up in here so that when we print the string, then it'll be set up, so we don't have to worry about. Just put strings. We don't have to worry about setting up the whole AX register, including AH. We'll put it in here first so that it's good. Okay, so, and then I just wrote this, so we're good. So let's go to print hex, give it another once over. I think we're good now. That probably didn't make sense what I said, but this should now print what we want here, 12AB. We're good. We're good. We got it to work. So that's how you print hexadecimal values. I know it was kind of scatterbrained and all over the place, but bear with me. Hopefully some to most of it was understood and you were okay with me making mistakes, because I'll definitely make mistakes trying to talk and do stuff off the top of my head, even though I'm using notes and references. But hopefully that's all right and you enjoyed it like I'm enjoying my nice, bitter, black as my soul coffee. So we're good there. But yeah, we can print hexadecimal stuff. We can print character strings. We're good. So where do we go from here? We're already including external files, so that's nice too. Where do we go from here? Well, at the moment, our BIOS, our boot sector, is only accessing the first 512 bytes. So even though we're including external files, it's the equivalent of putting their source code into here. We're still only using the first 512 bytes of our, of our boot sector. So what if we want to use more than that, or access other things like other disk drives, other data, and go beyond that 512 bytes? We have to use different things, and we need to access those somehow. So I'm going to go over that in the next part of this, which I think is, what is it called? Segment registers. So we'll go over segmenting segment registers to a limited extent and see how we can access other data beyond the first 512 bytes. Maybe contiguous, and I'll just access the next sort of area after the first 512, the next 100 bytes or something. And then maybe some other random location at hex, I don't know, some memory 20,000 or something. I don't know. Anyway. We'll go over addressing and segments in the next part, I think. We'll do that. But yeah, thank you for watching. I will see you on the next one.